right? We need to have a bit of an idea how that works, because that seems like a bit of an anomaly about what I see and what you see, but we're also going to explain that in terms of our muon example we had before. So the things we're looking at today, you need to be able to describe what proper length is, you need to be able to calculate length contraction, and we need to explain why we don't see those things in around an everyday situation. Obviously the answer is the same as the time. If you're dealing with simple velocities like we are every day, you're not going to get the amount of length contraction or time dilation that you would get if you were travelling anywhere near the speed of light. So we'll introduce some concepts and some examples where you can see that that's the case. So proper length, one thing that all observers agree on is relative speed. That's going to be our link today. We're going to come up with an equation where that is the comparison, the linking between those two things. And we say here that even though clocks are measuring different elapsed times for the same process, they still agree that relative speed, which is the distance divided by elapsed time, is the same. So if I'm travelling at 0.5 c, I know I'm travelling at 0.5 c. If you look at me travelling, you'll say that I'm travelling at 0.5 c as well. So the measurements you make are with respect to that 0.5 of the speed of light, and the measurements I make are with respect to that 0.5 c. That's a given that that I'm travelling, or we see that same velocity as the same velocity. You don't look at it and go, hang on a minute, you're travelling at less than no, I'm travelling at 0.5 c, and that's what I see, and that's what you know that you see as well. So if two observers see different times for an event, they must also see different distances for the relative speed to be the same for each of those, 0.5 c or 0.9 c, whatever it happens to be. So from our muon example yesterday, to an observer on the Earth, the muon is travelling at 0.950 the speed of light. And that takes a time that we measured from the Earth, 7.05 microseconds.